Now let's discuss G protein linked receptors as target of psychotropic drugs. Now to understand this, we have to first understand the agonist spectrum. Now the first scenario is that there is no agonist at the receptor. Now absence of agonist does not necessarily mean that nothing is happening with the signal transduction at a G protein linked receptor. Conformational changes may still be occurring at some receptor systems, but only at very low frequency. This is referred to as constitutive activity, which may be present especially in receptor systems and brain areas where there is high density of receptors. Now let's discuss what happens when an agonist is present at the receptor. Now an agonist produces a conformational change in the receptor that turns on the synthesis of second messenger to the greatest extent possible. The full agonist is generally represented by the neurotransmitter itself, but some drugs can also act in the same manner. Thus, an agonist triggers the full array of downstream signal transduction. There are two major ways to stimulate G protein linked receptors with full agonist action. First, several drugs directly bind to the neurotransmitter site and produce the same array of signal transduction effects as a full agonist. And secondly, many drugs can indirectly act to boost the levels of the natural full agonist neurotransmitter. Now this can be achieved by two methods. The first one has already been discussed, that is inhibition of monoamine transporters like SERT, NET, DAT and GAT1. And the second one is to block the enzymatic destruction of the neurotransmitters. Now let's discuss what happens when an antagonist is present at the receptor. In states of overstimulation, blocking the action of the natural neurotransmitter may be desirable. An antagonist produces a conformational change in the receptor that causes no change in signal transduction, including no change in the constitutive activity that may have been present in the absence of agonist. Thus, true antagonists are sometimes called neutral or silent, since they have no action of their own. Antagonists block the action of everything in the agonist spectrum. In the presence of an agonist, an antagonist will block the action of that agonist, but does nothing itself, as previously stated. The antagonist simply returns the receptor conformation back to the same state as exists when no agonist is present. An antagonist will also block the action of a partial agonist. Now, partial agonists are thought to produce a conformational change in the receptor that is intermediate between a full agonist and a baseline conformation of the receptor. And finally, an antagonist will reverse an inverse agonist. Now, an inverse agonist is thought to produce a conformational state of the receptor that totally inactivates it and even removes the baseline constitutive activity. Now coming on to partial agonists. These produce signal transduction that is something more than an antagonist, yet something less than a full agonist. This can also be seen as turning up the gains a bit from silent antagonistic actions, but not all the way to a full agonist. Now, depending upon how close this partial agonist is to a full agonist or a silent antagonist on the agonist spectrum will determine the impact of a partial agonist on downstream signal transduction events. For this reason, partial agonists are also called stabilizers, since they have the theoretical capacity to find a stable solution between the extremes of too much and too little. But they are also sometimes called weak, with the implication that partial agonism means partial clinical efficacy. And they can appear as net agonist or net antagonist depending upon the amount of naturally occurring full agonist neurotransmitter that is present. They can also appear as net agonists or net antagonists depending upon the amount of naturally occurring full agonist neurotransmitter. A partial agonist can simultaneously boost deficient neurotransmitter activity yet block excessive neurotransmitter activity, and thus may even be able to treat simultaneously states that are mixtures of both excess and deficiency of neurotransmitter activity. Now coming on to inverse agonists. Now these agents produce a conformational change in the receptor that stabilizes it in a totally inactive form. And thus the result of an inverse agonist is to shut down even the constitutive activity of the receptor system. Thus, in a sense, inverse agonists do the opposite of agonists. If an agonist increases signal transduction from baseline, an inverse agonist decreases it even below the baseline.